predicting the shapes of molecules. So Lewis theory can help us to predict the actual shapes of the molecules. Now, we did a lab on Wednesday where we made shapes, right? Balls and sticks. Now we're going to learn a little bit more about those. So there's a second theory that we use in conjunction with Lewis theory, and it's called valence shell electron pair repulsion theory. Okay, so we take the first letters of those, VSEPR. It's a little hard to pronounce, and so we tend to say Vesper, even though that's switching the E and the S. But we know what we mean when we talk about that. So instead of saying valence shell electron pair repulsion theory or saying VSEPR theory, we just say Vesper theory. This helps us to predict shapes. And again, it doesn't work for everything, but it works for a lot of things. So the basic idea here is that electron groups, and by electron group we mean a lone pair, a single bond, a double bond, or a triple bond. Each of those is considered one group of electrons. One group. That the electron groups repel each other. And if you think about this, electrons are negatively charged, right? So why would electrons want to be near each other? They really wouldn't. So we have these repulsions, okay? And so these electron groups are going to try to get away from each other, get as much space as possible. It's a little bit like siblings in the minivan, okay? They're not going to sit next to each other if they don't have to, right? They're going to spread out, or strangers on a bus. So let's look at how this works. Here is carbon dioxide. We have to have the Lewis structure to be able to predict shapes. So here's the Lewis structure. We've already learned how to do that. And then what we do is we look at the central atom. We're going to stick to looking at simple molecules for this class. We look at the central atom and we ask ourselves, well, how many electron groups are there? Well, this double bond is one group of electrons, and this double bond is one group of electrons. Because when we made those models, we had the bendy sticks, right? The gray sticks. And these two bonds were stuck between, well, I pointed on the wrong thing. I don't want to do that. Okay. Here they're not showing the double bond, but I could show the double bond. Let's do that. Let's see. So, really, there's a second bond there, right? So we had those two gray sticks. Can those gray sticks get away from each other? No, because they're both attached to the same atom at each end. So a double bond is two bonds, it's two pairs of electrons, but they're stuck together. And so that's one group. So we have one group here, and we have one group here, and they're going to get as far away from each other as possible, which is going to be on opposite sides of the central atom. So, one way you could think of this is that this is you and this is your ex-significant other who just turned out to be a real loser and you hate them, right? And so this is the planet Earth, and you're going to put as much distance as possible between you and this horrible person. So you're going to be on one side of the planet and they're going to be on the other side of the planet. Okay? You're trying to get away from each other. So I don't want to have anything to do with you. So we're going to think about how these things can get away from each other. So that's the farthest that two things can get away. They're still attached. You have to stay on the planet. Okay. So the angle, we talk about the angle, and the angle here is 180 degrees, which is a straight line. And so we say that carbon dioxide has a linear geometry. We look at these the whole molecule. We look at the individual atoms, and the atoms are all in a line. So we say this has a linear geometry. Any questions about that one? Let's look at another one. H2CO. I think you guys did this one in lab. I think you made a model of this one. So here's the Lewis structure. And when we're doing Lewis structures, it's entirely fine to make them flat and have right angles. I got on you on Wednesday about not having your model pictures look like you ran over them with a steamroller or something. to at least try to show them three-dimensionally. But when you're drawing Lewis structures, we're not really concerned about the shape. We're just concerned about where are the electrons and how are the atoms connected. So we look at the central atom and we see how many groups are there. Well, there's three. There's single bond, double bond, single bond. 3 groups. Now 3 groups are trying to spread out. They're all tied to this central atom, but they're trying to get away from each other. So they're going to spread out in a kind of a triangle shape. And the angles, here's the angle, is going to be 120 degrees for each of them. So they're putting an equal amount of space between each other. So we call this shape trigonal planar. Trigonal from the word triangle, and planar because this is flat. It's two-dimensional, it lies in a plane. So if you have 3 electron groups, you get a trigonal planar geometry. Any questions? Sometimes we have 4. Here is the Lewis structure for methane, CH4. It doesn't look real fancy because there's no lone pairs on it at all. But there's a carbon, and it has 4 hydrogens bonded to it. So we look at the central atom and we say, well, how many electron groups are there? There's 4 groups. How can 4 groups get away from each other? Well, if you're thinking two-dimensionally, you're going to think, well, that looks good. They're getting away from each other. This angle is 90 degrees. But molecules are not limited to 2 dimensions. They can go 3-dimensional. And you all had tetrahedrons in your hand on Wednesday. They looked like this, didn't they? There were a lot of things that looked like that. So this is 4 groups getting away from each other in 3-dimensional space. And it's a shape that we're really not familiar with. We understand a cube. A cube has 6 sides and each side is a square. A tetrahedron only has 4 sides and each side is a triangle. And there just aren't many of them around in real life. It's a weird shape. But you're just going to have to get your mind around it. This is a tetrahedron, and that's how those atoms get away from each other. Then the angle between them is 109.5 degrees. That's larger than if they were flat. This would be a 90-degree angle. They can get a little farther away by popping up into a tetrahedral shape. Okay? Any questions? So tetra is the prefix that means 4. A tetrahedron has 4 sides, 4 faces. Let's look at ammonia. Here's the Lewis structure for ammonia. Central atom is nitrogen. How many electron groups? Well, there's 4 groups, right? There's 3 bonds, and the lone pair counts also. The lone pair isn't attached to an atom, but it's there. It's a pair of electrons, and it's repulsive. Okay? So these 4 groups are going to form a tetrahedral shape. So now when we have lone pairs, we'll talk about electron geometry. This is the shape that the electrons make. So the electrons are making a tetrahedral shape. The lone pair and the 3 single bonds. They're getting away from each other in the shape of a tetrahedron. But when we talk about the shape of the molecule, those lone pairs are so tiny, they're basically invisible. So you arrange the electrons and say, well, this is tetrahedral, but then you say, yeah, but I can't see them. They're invisible. What shape am I left with? And that's this shape. And you saw shapes like that as well. Because the blue balls that we used in the lab had one of their holes plugged, right? That hole being plugged was the lone pair. When you draw the picture of it, it's just a little tiny bump on there, and it's not even worth drawing. We didn't draw those. So the shape we're left with here is called a trigonal pyramidal structure, or a trigonal pyramid. Trigonal meaning triangular, because if you look at these guys, there's 3 on the bottom, they'd form a triangle, and it's a pyramid. The central atom sticks up, it's not flat. Trigonal planar is flat like a piece of paper. If you could cut through all the atoms with one cut. This one you can't. If you could cut through 3 of them, but this 4th one is above that plane. Okay? So the lone pair is significant And I'm not going to hold you to this, but the lone pair actually is more repulsive than these bonds, and so it tends to squeeze these guys a little closer together, and so the bond angles here are not going to be perfectly 109.5. They're going to be a little bit less between the atoms and a little bit more between the lone pair and the atoms. And so that's why in Mastering Chemistry it may ask you what approximate bond angle it is, because we're not going to make you learn the actual bond angles. Any questions about that one? Let's look at water. Lewis structure for water. Water has 2 lone pairs on its central atom and 2 single bonds. So when we're thinking of Vesper theory, we're counting electron groups. This also has 4 electron groups. 4 electron groups make a tetrahedral shape, but now 2 of those corners are invisible. 2 of the corners are invisible, and so then when we look at what's left, when we make them invisible, we have this, and that has the very, very fancy name. It's bent. Okay, linear makes sense, bent makes sense. Okay, it's like a line, but it was bent. So again, it's the lone pairs that are causing this bend here. If there were no lone pairs, if we just had these 2 bonds, they'd be on opposite sides and it would be linear. And that's what they originally thought water was. But that doesn't match up with the properties of water. We know from experiment that water is not a linear molecule. And that's part of what helped develop Vesper theory. So here's a table which you may find very helpful as you're doing homework. Feel free to use the table starting out, but then wean yourself off of it. This is one of those subjects where I think if you think about what's going on, you have a central atom and you have electron groups, and then you're asking yourself, well, how many electron groups are they? How can they get away from each other as far as possible? What shape is that going to be? Are any of those lone pairs? If they're lone pairs, then we have to make those invisible, and then let's name the shape that's left. That's the process I go through in my mind to do this, because I'm not going to give you this table on an exam. But over here is the number of electron groups. That determines the electron geometry. So if there's 2, it's linear. If there's 3, it's trigonal planar. There's 2 different situations where we can have trigonal planar. And there's 3 different ones where we can have tetrahedral with 4. The difference comes when you have different numbers of lone pairs. These first 2 are going to have no lone pairs. Here, if you have 1 lone pair, you still have this trigonal planar electron geometry, but then the actual shape is bent because there's an invisible lone pair there. And then with the tetrahedral electron geometries, here we've got no lone pairs, there's 1 lone pair, and there's 2 lone pairs. Okay? That's kind of how the table works. So here are the instructions that your book gives you for predicting geometries. The first thing, you have to start with a correct Lewis structure. You look at the total number of electron groups around the central atom. A double bond is 1 group. A triple bond is 1 group. A lone pair is 1 group. A single bond, 1 group. And so then you figure out, okay, well, how are those going to arrange themselves? Then you see, well, how many lone pairs do I have? And then I cross this out because I don't think this is a good... Refer to table 10.1 to determine the electron geometry and molecular geometry. Well, that's great on homework, but a little work on an exam. So I cross that out. You determine the electron and molecular geometries by considering how those electron groups can get as far away from each other as possible. Okay? Let's do some examples. Let's predict the molecular geometry of ClNO. And we're told that nitrogen is the central atom. Sometimes it's not going to be obvious to you which one should go in the middle, and when that's the case, we'll tell you. So we're told that nitrogen is in the center. So there's not a good color. Nitrogen in the middle. We need a Lewis structure to start with. So we start with a skeletal structure Chlorine on one side, oxygen on the other, because we're told nitrogen is the central atom. Then we have to figure out, well, how many electrons do we have to place? Chlorine has 7, nitrogen has 5, and oxygen has 6. There's no charge, so we add those two together and the 3 together, and we get 18. 18 valence electrons. So we have to have a bond here and a bond there. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18. Is this looking kind of familiar? The SO2 did this, the NO2 minus did this, the ClNO does this. We've got 3 atoms and the same number of valence electrons. The arrangement of the electrons is going to be the same. But here we have 2 different atoms bonded to the central atom. We're going to have to make a double bond, but they're not the same. So maybe it makes a difference which one we give the double bond. Your book does not go over this, and I wish they would. I should really just throw in a slide, but I'll explain it to you right here. Let's look at nitrogen, oxygen, and fluorine. So nitrogen is in group 5. It has 5 valence electrons. So when we draw the Lewis structure for just a nitrogen atom, we get 1, 2, 3, 4, 5. How many of those electrons are not paired? 3 of them, right? Nitrogen tends to form 3 bonds. Each of those unpaired electrons tends to form a bond. How many valence electrons does oxygen have? 6. 1, 2, 3, 4, 5, 6. Oxygen has 2 unpaired electrons. It tends to form 2 bonds. Fluorine has 7 valence electrons. So it has 1 unpaired electron, and it tends to form 1 bond. Fluorine, chlorine, bromine, iodine, all the halogens have 7 valence electrons. They all have 1 unpaired electron. They tend to form 1 bond. So if we're choosing where to put the double bond between chlorine that likes to form 1 bond and oxygen that likes to form 2 bonds, where should we put it? We should probably give it to the oxygen, right? Because this is a situation where those atoms are not identical. So we're going to put the double bond here, and then I have to erase a pair of electrons so that we have the right number. Now look, how many bonds does nitrogen have? It's got 3, right? 2 on one side and a double bond, and 1 on the other. That's what nitrogen likes to do. There are exceptions, but nitrogen tends to form 3 bonds, oxygen tends to form 2, and all the halogens tend to form 1. So here's our Lewis structure. And sometimes you're doing a problem and you're like, great, I got the Lewis structure. Oh, wait a minute, that wasn't the end of the question. That was just the first step, right? Lewis structure. Okay, now what do we do? Now we say, what are you doing? What's wrong with that structure? What's wrong with it? There's something wrong with it. Nitrogen's got too many electrons, and who doesn't have enough? Chlorine. His teacher screwed up. So we gotta fix that. Pencil is good for Lewis structures. Okay, so let's double check. Everybody's got 8. Okay. You gotta have the correct Lewis structure, it's not gonna work. Now we're gonna look at the central atom, nitrogen, and ask ourselves how many groups of electrons? 1, 2, 3. 3 groups of electrons. And so when we draw, we could draw the electron geometry. So here's the nitrogen in the middle, and we're going to have 3 groups that are trying to get away from each other. Okay? That's what the electrons do. Now, where are the atoms? Well, there's an atom in the middle, and there's an atom at the end of one of these, and there's an atom at the end of the other one. And what's at the end of the other line? It's a lone pair. Okay, I picked green for a reason here. You know, the green screen technology that they have, that's how they do the weather maps on TV. Everything that's green basically disappears, so the green is disappearing. So we can see these guys, but we can't see the lone pair. Okay? This sort of has some strange and not really correct, but I'm sorry, I'm just going to go there anyway. Okay, so in society, you know, you've got married couples and you've got single people, right? The single people are a little bit like lone pairs. And sometimes they feel like maybe they're a little more repulsive because the married couples tend to go off by themselves and exclude the single people, which is not right and it shouldn't happen, but you know, it sometimes does. And sometimes they may also feel like they're invisible. Like all of society is catering toward people with families and children, and they're just kind of left out. So here we have an illustration of that in the chemical world. There's our lone pair, and he's feeling very invisible. Okay, so when we're looking at the shape of the molecule, we don't see the lone pair. He's there, he's pushing those other atoms together, but we don't see him. So what's the shape? Just looking at the orange stuff, what's the shape of that? It's bent. So the shape of the molecule is bent. You see how I did that? That's the process. Any questions? Let's do the SO32 minus ion. What's the name of that ion? Sulfite. So first step is a correct Lewis structure. We're going to put the sulfur in the middle. Be symmetrical, and it's got 3 oxygens around it. If you want to put your third oxygen on the top, or if you want to have the empty one on the right or the left, it doesn't matter. And then we have to consider how many valence electrons are there. Well, the sulfur has 6, and there's 3 oxygens, and they each have 6. What do we do with that 2 minus charge? We add 2 electrons, so plus 2. So 3 times 6 is 18, plus 6 is 24, so we've got a total of 26 electrons. Did I do that right? My mental calculator is not functioning well today. 26 electrons to mess around with. So we're going to start with a single bond between each of these. Never start with double bonds. Start with single bonds. So I've got 2, 4, 6 from the single bonds. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Nice. There were enough that time. That's why you don't want to start with a double bond, because what if you don't need it? Then it's just going to be harder later. And then we need brackets and indicate the charge. And just a reminder, in Mastering Chemistry, there's no way for you to do the brackets. You still do the charge, but just be okay with not having brackets. And don't text me and say, I can't do the brackets. You can't do the brackets. It's okay. So there's our Lewis structure. We're predicting the molecular geometry. How many groups of electrons? 4. Okay, so I'm going to draw a tetrahedron. So there's 1, 2, 3, 4. So this hashed one, we'll see it in a slide coming up soon. We envision that as coming out of the screen. I'm sorry, that's the wedge. The hashed one, the dashed one, is going behind the screen, And these two guys are in the plane of the screen. So that's one way to draw a three-dimensional thing on a flat piece of paper. That's the electron geometry. It's tetrahedral. There's 4 groups. And then let's draw in the atoms. Well, there's the sulfur in the middle, and there's an oxygen over here, and an oxygen over here, and an oxygen over here. And up at the top is the lone pair. Let's draw the lone pair. But he's invisible. So we look at just the orange ones, and we say, well, what shape is that? It's trigonal, right? It's triangular. Is it flat like a plane? No, it's pyramid. So trigonal pyramid or trigonal pyramidal. The exams are multiple choice, so if you can recognize the difference between pyramidal and planar, you're good. There will be no pronunciation quiz. Okay. Any questions about that one? I know we're out of time. Just real quick, this is the hashed lines and the wedged lines that show coming out of the two-dimensional surface, whether it's your paper or the screen, and going into. And this is how your book illustrates those different geometries.